by the end of this tutorial, you should be able to graph any logarithmic function. Okay, so we're going to start with this one that you see listed, y equals 5 minus the ln, the natural log of x plus 2. Okay, I also included the transformation rules that you learned way back in chapter 3, I believe, but it was early on in the school year. And we've been using these transformation rules for each of the functions that we've been studying, from polynomial functions to rational functions to exponential and now to logs. So the first thing that I would do here in graphing this particular function is I would try to remind myself, well, what in the world would the graph of y equals ln of x be? And so this is important that you understand that the graph of ln of x actually is doing a poor job here. It's going to come out here like this and look kind of like that. Now I always draw them pretty sloppily when I'm drawing them dotted, but nevertheless that is what the graph of the ln looks like. And keep in mind that the y equals ln of x has a vertical asymptote at x equals 0. So the y-axis is the vertical asymptote for the log functions. And remember, guys, log functions look like that. In other words, draw the L really long like that to remind you that there will be a vertical asymptote. So given that, our key point is what we want to keep track of in addition to where that vertical asymptote is moving. So our key point being at 1, 0 on the graph of ln of x. The first transformation that we're going to apply to y equals ln of x is y equals negative ln x. So negative ln x, minus sign in front of the function, it means that we reflect. It's an outside, so can't get my thumbs in there, but it's an external or an outside transformation, and that means an up and down. And the up and down transformation means going this way, and if you're going to reflect a graph about an axis, the axis that you cross when you go up and down would be the x-axis. So any of the graph of this one here that's below the x-axis is now above the x-axis. So we're going to draw it like this. Any of the part of the graph of ln that's above now is reflected below the x-axis. So this green graph is negative ln x. Y equals negative ln x. Okay? So we took care of the negative in front of the function, and now we're going to apply the x plus 2. So inside the parentheses now, to the green graph, we're going to add 2 inside parentheses, right? Instead of it being x right there, it's an x plus 2. And so that tells us we're going to move this entire graph, the green one, to the left 2 units. Keep in mind, the first transformation that we applied did not change the coordinates of our key point. Okay, our key point is on the x-axis, and if we reflect about the x-axis, that's not going to change. But our next one we're going to draw in purple. Okay, and we're going to go over here 2 units to the left, and our key point just moved 2 units to the left. And remember, guys, that the vertical asymptote and the key point are always going to be 1 unit apart. And so our vertical asymptote moving 2 units to the left becomes x equals negative 2. Now I'm writing this in right now because I know that when I apply my last transformation, it's not going to change the vertical asymptote, so I don't mind drawing that now. So again, moving this green graph to the left 2 units, the entire graph moves to the left. And I don't worry about the x-intercept yet. Now that's what that looks like. So that purple graph now is the graph of y equals negative ln of x plus 2. So we're actually doing 1, 2, and then 3 problems all in one. So if you apply just one transformation, then you get the green one, 2, you get the purple one, and then finally we're going to draw the graph of y equals 5 minus ln, and the 5 minus the ln, that 5 and we can put it as 5 minus or negative ln of x plus 2 plus 5, which would mean we're taking the current function and adding 5, which means we take this graph and we move up 5. Okay? And so, what color should we use here? Let's use, I hate to use black, so I guess I'll have to use red. Alright, so moving this key point up 1, 2, 3, 4, 5 units, the key point has coordinates -1, 5. Okay, so that's really important. And it's important because going through that key point, the graph drastically changes. Okay, so if we look at the graph of the function, we have the vertical asymptote. And the function, for the most part, stays relatively close to that vertical asymptote until it hits the key point. So once it hits the key point, then it kind of takes off. Okay, and that's the graph. Right there. Takes off, goes through the key point. But let's make sure we understand all the parts of that. So anyway, yeah, that's the graph of y equals 5 minus ln of x plus 2. That's it. Solid one, red. Okay. And again, let's fill out this chart here. Domain. The domain of the log is, you can even do the domain without graphing it. I would encourage you to do that, is because you're going to get some problems that ask you just to find the domain of the function. You're not going to want to have to graph it. You really don't need to do that. You could, and this would be a good way to check to see that your graph is right. Don't even look at the graph. Figure out what the domain is, because you know how to find the domain of a log function. Okay, the domain of the log function, and maybe you do the work down here. I don't know where you want to do it. Let's see, domain. Let's do it up here. Okay, so the domain is this log function. We know that whatever we take the log of, which is called the argument, must be non-negative. It must be greater than 0. So therefore, x must be greater than -2. X must be greater than -2. Well, is it? Yeah, it is. So we're good so far. Now the range of the log function is always all real numbers. Okay, all real numbers. Increasing. Is this function increasing at all? If we look at the graph, we see as we're moving left to right, the y values are getting smaller. So no, it's not increasing anywhere. Increasing nowhere. Decreasing over all real numbers in the domain. So be careful there. You don't want to just say all real numbers. It's all real numbers in the domain, and it's usually better to write it kind of like this, interval notation for the decreasing and increasing. Horizontal asymptote. Well, there is no horizontal asymptote with logs, but there is a vertical asymptote with there is a vertical asymptote with logs, and the vertical asymptote has an equation. Okay, make sure you always write that as an equation. Don't just write -2. X-intercept, well, yes, it will intercept the x-axis, and this is usually the trickiest part because it also involves solving a logarithmic equation. So the x-intercept, remember, that's when we let y equal 0. Okay, whereas the y-intercept, we let x equal 0. Okay, so the y-intercept letting, x-intercept letting y equal 0, we solve the equation. We're going to do it down here. 0 equals 5 minus the ln of x plus 2. Bringing the ln over to the left. ln of x plus 2 equals 5. We then have a log statement. We want to free up that x, right? We want to make sure that we have access to that variable right there. It's in the argument. So to unlock that, we convert to exponentials, and we get e to the 5th power is equal to x plus 2, and therefore x equals e to the 5th minus 2. We don't even need to know what that is. We just write e to the 5th minus 2. Okay, the y-intercept, just let x equal 0, and if you look at the equation, x equals 0, we get 5 minus ln of 2. Okay, and again, no max, no mins, and I'm trying to rush here to get it under the 10-minute mark. And the key point, again, is at -1, 5. Nice job.